Hello everyone. So today we'll start a new chapter which is Laplace transform. Pierre-Simon Marquis de Laplace. He is a scientist, mathematician, astronomer and physicist who was born on March 23rd, 1749 in France. He is known by his investigations into the stability of the solar system. So he is the father or the creator of the Laplace transform. And then it was developed by the British physicist Oliver Heaviside between the 18th and the 19th century to simplify the solutions of many differential equations that describe physical processes. So for more information about this personality of Laplace, you can check the Encyclopedia Britannica 2007, and you see here the link to these reports. You can learn about this big personality in mathematics and applied mathematics. Oliver Heaviside is a British scientist. He was born on May 18, 1850 in London, England, and he died on February 3rd, 1925. So this scientist has devoted himself to the investigation of electricity, and he used the Laplace transform in operational calculus, and he has used extensively the Laplace transform to study the transient current in network. Okay, so his work is also on the theory of the telephone made long distance service practical. So for more information, you can visit this website to learn about this scientist and his achievements. I will start with the definition of the two-sided Laplace transform. So I will note LB of ft, so the transform, the bilateral transform of ft, to be the integral minus infinity plus infinity ft exponential minus st. So here S is a complex which is composed by a real part and imaginary part. And this is the main difference between the Fourier transform and the Laplace. So we see here the sigma plus j omega. So the real part is sigma, and the imaginary part of this complex S is equal to omega. So if we write, so here there is a minus missing. So the Fs, it is a complex which is obtained from the integration from minus infinity to plus infinity, ft exponential minus st, where s is sigma plus j omega. So if I will split ft, I will decompose an exponential in two terms. I will have ft exponential minus sigma t times exponential minus j omega t. So here we see that this bilateral or two-sided Laplace transform, it is exactly the Fourier transform of ft times exponential minus sigma t. The inverse Laplace transform is given by this definition. So by the way, we will not use in this basic course of signals and systems this integral formulation to get the inverse Laplace transform of ft. We will use the properties of the Laplace transform in order, and also we may use function decomposition into simple rational terms in order to identify the inverse Laplace transform. If I will split the bilateral Laplace transform into two parts, which is integral minus infinity to 0 ft exponential minus st, plus the integral of ft from 0 to plus infinity. We are interested always in signals that starts from t equal to 0 to plus infinity. So the negative part of the signal will not be included. So here we will assume that ft is 0 for time negative. In this case, this part of the integral will be 0, and we will be left only with this part, which is the integral 0 infinity ft exponential minus st dt, where the s is a complex equal to sigma plus j omega. So we will adopt this notation to say that ft has a Laplace transform which is equal to fs, and fs by the inverse Laplace transform gives ft. Integration from 0 to plus infinity is like we have one side, so we can say one side Laplace transform or the unilateral Laplace transform. And this is the well-known definition of the Laplace transform, which is integral 0 plus infinity ft exponential minus st dt. So in studying Laplace transform, we assume that the S has a real part and imaginary part. And here I am in the complex plane where I have S, we say the S plane, the S domain, or the frequency domain. And here we have a real part and imaginary part. So in this quadrant here, we have both real part and imaginary part positive. Here we have real part negative, imaginary part positive. And here we have both of them, the real part and the imaginary part are negative. And in this part, we have imaginary part negative and real part positive. The signal ft may be singular at time t equal to 0 because in reality, always we switch at time t equal to 0 to some value. Because when we study realizable systems, the signal or the system will not react if we speak about causal systems and causal signals. So the system is not responding when time is negative. So this is why we may have a jump of a signal at time t equal to 0. So in that situation, we can define the inverse Laplace transform of fs to be ft when time is positive, to be the half of the value at time t equal to 0, because we have a jump, so we will take the average value, which is f of 0 plus over 2 at time t equal to 0, and ft is 0 when time is negative. The condition of existence of the Laplace transform is the boundedness of the signal ft by an exponential function of time. So if there exist two real m and alpha such that the absolute value of ft is less than m exponential alpha t, so m is positive and alpha it could be positive or negative. It means that all signals that can be bounded by an exponential function, their Laplace transform exists. As we did for the Fourier transform, we start with the linearity property. It means if I have two signals, f1 and f2, and I will compose the Laplace of the sum. So the Laplace of the sum will be the sum of each Laplace. And here we see that this integral can be split into two terms like here. And this term and this term are exactly the Laplace transform of f1 plus the Laplace transform of f2, which means f1 of s plus f2 of s. If I will multiply now f1 by certain coefficient, f2 by another coefficient, we will see those coefficients appearing here. And this is what we call here the linearity property of the Laplace transform. The step function, which has a terminal value equal to 1 and a step time equal to t0, is plotted in the right-hand side as shown here. So the step time is t0, and then at 1 it is 1 forever. So this step function is one of the basic functions that we use extensively in studying systems and signals. So here we will calculate its Laplace transform. So the Laplace of ut, okay, when t0 is equal to 0, it is the integral 0 infinity, the step function ut exponential minus st. So at time t equal to 0 to plus infinity, I will replace ut by 1. So I will integrate now this function exponential minus st, okay, from 0 to plus infinity, which gives 1 over minus s exponential minus st, taken from plus infinity to 0. So here we have a limit, okay, and this limit will exist when the real part of this complex is when we have here s to be sigma plus j omega. If the real part of the s is positive, so the limit here is equal to 0. And here we have minus 1 times minus 1 over s, which gives these results. So the Laplace transform of the step function of step time t0 equal to 0 is equal to 1 over s under the condition real of s is greater than 0. So that you know that this limit will not exist. So this limit is not equal to 0, okay, until we have the condition real of s positive. If the real of s is positive, and this is the condition of the convergence, so we will have now ut to be 1 over s, okay, ut equal to 1 over s. If we take now an exponential function, exponential minus at, okay, t positive, and I will calculate the unilateral Laplace transform. So I will have exponential times exponential, so I can gather the exponentials like this. And then I will integrate with respect to time, so I will have 1 over minus s plus a, the same function, evaluated from plus infinity, from 0 to plus infinity. So here, if the real of s plus a is positive, so this limit will be 0 at infinity, and we will be left only with the term minus times 1 minus over s plus a, which gives 1 over s plus a. So any function of the form exponential minus at, okay, times ut has a Laplace transform equal to 1 over s plus a. I will invite the student to use MATLAB in order to evaluate and check the results using the symbolic package of MATLAB. So here I am showing the basic instructions to be followed in order to get the Laplace transform from MATLAB. So first of all, MATLAB evaluates only, okay, numerical values. Okay, so we need to declare that f, t, and a are symbolic values. So this is why we start with the instruction sims fta. It means consider f, t, and a as symbolic values. And then I will define f now here, exponential minus a times t. You see, if you start by writing this instruction before this, so you will get an error message from MATLAB saying that we need values to be incorporated inside the exponential. Otherwise, this cannot be defined without preceding this instruction by declaring ft and a as symbolic values. And then at this line, I will calculate the Laplace of f. So I will invite the student to use these instructions in order to get the symbolic expression of the Laplace transform, or to check their assignment and homework with this instruction. I will start with the differentiation property of the Laplace before giving the rest of the properties, because the differentiation property is seen in solving of differential equations. So here I will start from the definition of the Laplace, and then I will integrate this function, okay, using integration by parts. So I will set u to be ft and dv to be exponential minus st dt. According to this definition, so du over dt will be df over dt, and the v will be the integral of this, which gives exponential minus st over minus s. So now, by using integration by part, so I will have uv here between 0 and plus infinity, and v du here under the integral 0 plus infinity. Okay. So if you see here, this part, it is exactly the Laplace transform of df over dt. So this is the definition of the Laplace transform of the derivative of f with respect to time. And here I have some value of f at time t equal to 0, which is appearing from here, assuming that exponential minus st at plus infinity is 0, because the real part of the s is negative. I'm sorry, the real part of s is positive, multiplied by minus will be negative, and this will lead to the limit at plus infinity equal to 0. So if I will multiply now, fs is equal to this. It means sfs will be equal to f minus f of 0 sfs, okay? Okay, which means that the Laplace transform of this will be sfs minus f of 0, okay? So fs equal to this, multiplying by s both sides, and we will bring this term to the other side. We will have the Laplace transform of df over dt, which is this expression, will be equal to sfs minus f of 0. But as we said that the signal may be discontinuous at 0, so we will be interested in only the value at time t equal 0 plus. It means just after the time t equal to 0, and we will record now the result as it is. It means the Laplace transform of df over dt will be sfs minus the value of the function at time 0 plus. Maybe the function at time t equal to 0, okay, is equal to 0. In this case, f of 0 is equal to 0. If there is discontinuity of the f at time t equal to 0, we will take the value at 0 plus. How can we prove now the nth order property of the differentiation of a function with respect to time, nth time, okay? So here we can record the results as it is, okay? But we can prove it step by step by following the integration of the Laplace transform, second and third until the nth order. So here, if I will start, okay, from here, okay, So I can start from fs equal to this, okay, and then use integration by parts for this by taking u to be df over dt and v to be exponential, or dv exponential minus st dt. So du will be the second derivative of f, okay, v, and we will continue the integration as we did for this case. So by continuing now differentiation by part, we will arrive to these results. So it is easy to memorize it. So the Laplace of the nth derivative of f with respect to time will be Sn, so the n which is here, we start with it, Sn fs, and the rest are what? Are all dependent on the initial condition of f, f prime, f n minus 1. So what you are seeing here, so f prime, it means df over dt, okay? And f between brackets n minus 2, it means differentiation of order n minus 2 of f with respect to t n minus 2. And here we have differentiation of order n minus 1 evaluated at 0 plus. So we will start from the higher parameter n of differentiation, and then we will reduce, and we keep minus always. So minus s n minus 1 f of 0 plus, and then I will decrease the power of s by 1, and I will replace f by f prime, and I will decrease the order of s until I will have s power 0 differentiation n minus 1 at time equal to 0 plus.